If someone had said in the early 19th century that cars would one day be powered by electricity, they would probably have been laughed at. But the truth is that this idea started taking shape more than 200 years ago. In 1801, Alessandro Volta introduced his electric battery, a milestone that paved the way for all modern batteries. Decades later, in 1832, the first electric vehicle was developed, but it was still a rudimentary invention, incapable of competing with combustion-powered vehicles, which would dominate the streets by the late 19th century. As promising as electric vehicles seemed, the biggest problem was the same that haunts any new technology: battery limitations. The major setback came in the 20th century, with the invention of the internal combustion engine and the development of petroleum infrastructure. Electric cars were sidelined. For decades, this technology was practically forgotten, while gasoline and diesel-powered engines became the backbone of the automotive industry. It was only in the late 1990s and early 2000s that efforts to bring electric vehicles back began to emerge. However, there was still a long road ahead. Batteries at the time were expensive, bulky, and had extremely limited range, making the widespread adoption of electric vehicles unfeasible. The turning point came in 2008 when a small and daring automaker decided to challenge the dominant logic. Tesla launched the Roadster, a fully electric sports car that shocked the world by offering a range far superior to any other electric vehicle ever produced. And the secret behind this breakthrough was in the battery technology. Instead of following the traditional path, Tesla bet on cylindrical lithium-ion cells, the same ones used in laptops and electronic devices, but applied on a much larger scale. With 6,831 Panasonic 18650 cells, the Roadster managed to deliver unprecedented performance, putting Tesla on the map of the automotive industry. The success of the Roadster paved the way for the launch of the Model S, an electric sedan that redefined the concept of a premium battery-powered car. Unlike electric vehicles of the past, the Model S proved that performance, luxury, and range could coexist in a single vehicle. It not only outperformed many combustion engine sports cars in acceleration, but also offered a range capable of covering long distances without constantly relying on recharges. This model was a game changer, showing that Tesla was not just trying to compete with traditional cars, but was actually changing the way people viewed electric vehicles. The impact was so profound that Tesla quickly expanded its lineup, launching the Model X, an electric SUV featuring Falcon Wing rear doors and an even larger battery capacity. But the real breakthrough came with the Model 3, the car that democratized electric technology. Unlike the previous models, which had high price tags, the Model 3 was designed to be accessible to a much larger audience. With this move, Tesla transformed what was once a niche into a global phenomenon, forcing traditional automakers to catch up and invest in their own electric models. Tesla is expanding its battery production at an impressive rate. Although it has not yet reached the 536 cells per second mark, the company has ambitious plans to drastically increase its manufacturing capacity in the coming years. Currently, Tesla is working to expand its annual battery cell production to 100 gigawatt hours, which translates to approximately 3,170 cells produced per second. And this is just the beginning. By 2030, the company aims to reach 3 terawatt-hours per year, which would increase production to a staggering 95,000 cells per second. This scaling effort started years ago when Tesla used 18,650 cells, originally developed for consumer electronics and later adapted for the first Model S and Model X. While efficient, these batteries had limitations in terms of large-scale production. In 2017, Tesla introduced the 2170 cell, a new format that provided higher energy density and lower costs. This model was adopted for the Model 3 and Model Y, enabling an increase in range and efficiency. But the company's innovation journey did not stop there. At the Battery Day event in 2020, Tesla unveiled its newest bet, the 4680 battery. This revolutionary design introduced a tabless structure, which enhances efficiency and reduces manufacturing costs. The biggest difference in this new format is its size. Compared to the 2170, 4680 cells are much larger, meaning fewer units are needed to assemble a single battery pack. This simplifies vehicle assembly and reduces the number of internal connections, improving thermal efficiency and overall performance. The 4680 battery was promised to make battery production cheaper and more efficient, paving the way for the long-awaited $25,000 Tesla. However, transforming an innovative technology into a mass production process is not that simple. Tesla faced significant technical challenges, particularly in adopting dry electrode technology, a method that can drastically reduce costs and the environmental footprint of battery production. Despite the difficulties, the company continued to refine its processes, and gradually, the production of 4680 cells began to scale up. Beyond improvements in cell design, Tesla is also diversifying the chemistries used in its batteries. One of the most significant recent advancements has been the adoption of LFP, lithium iron phosphate, batteries, which have lower production costs and a longer lifespan compared to traditional nickel-cobalt batteries. These batteries are already being used in Model 3 and Model Y standard range in China and are gradually being tested in other markets. This strategic shift has a clear motivation: to reduce reliance on expensive materials and ensure a more stable battery supply. If there is one thing that defines Tesla, it is its constant pursuit of innovation. But creating more efficient batteries is not enough. Ensuring that the essential materials for their production are available at scale is crucial. After all, each battery cell depends on lithium, nickel, cobalt, and graphite, and any supply chain disruption could compromise the entire production process. To avoid this risk, Tesla has adopted a bold strategy: verticalizing the process to gain control over the extraction and refining of these raw materials. Lithium, for example, is one of the most critical elements in lithium-ion batteries. It serves as the primary charge carrier within the cell, allowing energy to flow efficiently. However, mining and refining lithium are time-consuming and costly processes, heavily dependent on a few global suppliers. To reduce its dependence on third parties, Tesla announced the construction of its own lithium refinery in Texas, a project designed to strengthen its independence in securing this essential element. Another indispensable material is nickel, which increases battery energy density and improves the range of electric vehicles. However, its mining has posed significant environmental and cost challenges. Tesla has been encouraging suppliers to adopt more sustainable practices while also seeking alternatives to reduce nickel usage in some of its battery chemistries. Cobalt, in turn, is one of the most controversial components of modern batteries. Primarily extracted in the Democratic Republic of Congo, this metal has been associated with human rights violations and severe environmental impact. To address these issues, Tesla has been investing in the gradual reduction of cobalt usage in its batteries while forming partnerships with responsible mining suppliers. This initiative is an important step toward making battery production more sustainable and ethical. But one of the most intriguing shifts in Tesla's strategy is the adoption of LFP, lithium iron phosphate batteries. Unlike nickel-cobalt batteries, LFP batteries do not require cobalt and are cheaper to produce. Additionally, they have a longer lifespan and are safer, as they have a lower risk of overheating. Due to these advantages, Tesla started using them in standard range versions of the Model 3 and Model Y in China, and there are indications that this technology will be expanded to more markets. Meanwhile, Tesla is closely monitoring the development of solid-state batteries, which have the potential to revolutionize the industry. This technology would replace the traditional liquid electrolyte with a solid material, eliminating leakage risks and dramatically increasing energy density. This means that vehicles could travel much longer distances on a single charge, while batteries would become more durable and safer. Although still in the experimental phase, the potential of solid-state batteries is so significant that several companies, including Tesla, are keeping a close watch on their progress. Producing batteries at a large scale requires not only a constant supply of raw materials, but also a highly specialized refining process. To transform mined lithium into a usable material, it goes through several stages of purification and chemical treatment. This process includes separating positive and negative electrodes, as well as applying metallic coatings to enhance energy conduction efficiency. Tesla has been investing heavily in research to make this process faster, cheaper, and more sustainable, minimizing the environmental impact of battery production. Producing batteries at scale is not just a matter of quantity. Each manufactured cell must be efficient, safe, and durable enough to withstand years of intensive use in electric vehicles. And this is precisely where Tesla is redefining the game. Instead of simply purchasing ready-made batteries from suppliers, the company has developed its own manufacturing process, eliminating unnecessary steps and optimizing every stage of production. This not only reduces costs, but also ensures superior battery performance. The process begins with lithium refining, an essential step in transforming raw mined material into a pure, usable chemical compound. This is one of the most critical aspects of battery production, as any impurity can compromise cell efficiency. Tesla has been heavily investing in this stage, even building its own lithium refinery in Texas, ensuring a stable and high-quality supply. Once refined, lithium is combined with other materials such as nickel, cobalt, and graphite, forming the essential components of the battery. The next step involves applying these materials to the positive and negative electrodes, creating the internal structure of the cell. Traditionally, this process required multiple layers of liquid coatings, but Tesla is advancing in dry electrode technology, which significantly reduces manufacturing time and costs. With the electrodes ready, cell assembly begins. The layers of electrodes and separators are stacked or rolled, forming the core of the battery. Each cell undergoes an initial charge and discharge cycle, an essential process to ensure that the battery functions correctly and has a long lifespan. This stage also allows for the identification of defects and the removal of cells that do not meet quality standards. After the production of individual cells, they're organized into modules and battery packs. In the past, electric vehicle batteries were composed of multiple interconnected modules, but Tesla introduced an innovative concept, cell-to-pack (CTP). This method eliminates the need for intermediate modules, reducing weight and increasing the battery's energy density. In other words, vehicles can store more energy without increasing the size of the pack. This advancement is crucial because Tesla's electric vehicles require a massive number of battery cells. For instance, the Model 3 and Model Y standard range use approximately 2,976 cells, while the long-range versions require 4,416 cells. Meanwhile, the Model S and Model X require 7,180 cells, and the Cybertruck, depending on the version, may need over 1,300 cells. Multiplying these figures by the millions of vehicles Tesla plans to sell annually, it becomes clear that the demand for batteries is colossal. However, Tesla does not produce batteries only for its cars. The company's energy storage division, which includes products like Powerwall and Megapack, has already surpassed the demand for automotive batteries. This means that, in addition to the billions of cells needed for its vehicles, Tesla must also manufacture billions of additional cells to support its growing energy division. As much as Tesla is expanding its battery production capacity, the company still relies on strategic partners to meet growing demand. After all, large-scale battery manufacturing involves not only assembling cells, but also securing raw materials and specific components. To ensure a stable and diversified supply, Tesla has formed partnerships with some of the world's largest battery manufacturers. Panasonic is one of Tesla's oldest partners. The relationship between the two companies began more than a decade ago and was fundamental to the development of the first batteries used in the Roadster and Model S. Panasonic supplies lithium-ion cells directly from Gigafactory, Nevada, one of the world's largest battery factories. As production has grown, this partnership has strengthened, ensuring a continuous supply for Tesla's best-selling models. Another major player in this list is LG Energy Solution, a division of the South Korean giant LG. Unlike Panasonic, which mainly works with cylindrical cells, LG Energy also supplies prismatic and pouch batteries, which are used in some models manufactured at Giga Shanghai and Giga Berlin. LG Energy's presence in Tesla's battery portfolio helps diversify battery options and increase production flexibility. Meanwhile, China's CATL, Contemporary Amperex Technology Company, Limited, has become a key player in Tesla's strategy, especially regarding LFP, lithium iron phosphate batteries. These batteries, which have a lower cost and longer lifespan compared to traditional nickel-cobalt batteries, are widely used in Model 3 and Model Y standard range. Tesla is betting on these batteries as a more affordable solution for entry-level vehicles, allowing the company to lower prices without compromising durability. But one of Tesla's most unexpected partnerships is with BYD, Build Your Dreams. BYD is not just a battery supplier. It is also one of Tesla's biggest competitors in the global electric vehicle market. Despite this, the two companies signed an agreement for BYD to supply Blade batteries, a highly safe and efficient LFP battery technology. This partnership, although unusual, shows that Tesla is willing to work with competitors to secure a robust battery supply. Beyond these major manufacturers, Tesla also collaborates with smaller companies, such as Samsung SDI and Eve Energy, which provide batteries for specific markets and applications. Diversifying suppliers is crucial for mitigating risks, especially in a sector so dependent on scarce raw materials and global supply chains. Relying on external suppliers can be a major risk, especially in a market where the demand for batteries is growing exponentially. Tesla is well aware of this, which is why it has been heavily investing in becoming self-sufficient in battery manufacturing, reducing its dependence on companies like Panasonic, CATL, and LG Energy. This move is not just a commercial strategy. It is a necessity to ensure production stability and cost reduction. Since acquiring Maxwell Technologies in 2019, Tesla has been working on improving dry electrode technology, a method that promises to revolutionize battery manufacturing. Unlike conventional processes that use liquid solvents and require multiple drying stages, the dry electrode method eliminates these intermediaries, making production faster, cheaper, and more sustainable. This innovation could be a game changer for Tesla, allowing the company to increase its production capacity without the need for massive factory expansions. Another major breakthrough in Tesla's quest for self-sufficiency has been the large-scale production of the 4680 battery. So far, Tesla has already manufactured more than 100 million 4680 cells, and the company's plans are even more ambitious. Tesla intends to expand the production capacity of this battery at Gigafactory, Nevada, with a goal of reaching 100 gigawatt-hours per year, enough to power 1.5 million electric vehicles annually. However, the scalability of this new format still faces challenges, particularly in dry electrode production and the optimization of manufacturing processes. Despite all these advancements, Tesla is still unable to produce all the batteries it needs in-house. The company continues to rely on suppliers like Panasonic and LG Energy to complement its production and ensure that its vehicles can be delivered on time. However, Tesla has made it clear that its goal is to gradually reduce this dependence, investing in the construction of new factories and improving its internal processes. Beyond producing battery cells themselves, Tesla is also expanding its control over the raw material supply chain. One of the most emblematic examples of this strategy is the Lithium Refinery in Texas, which has already begun producing its first shipments of refined material. This refinery is expected to supply enough lithium to power millions of batteries per year, ensuring that Tesla has a stable and secure source of this essential resource. The company is also exploring new battery formats and chemistries, such as the already mentioned LFP, lithium iron phosphate batteries, which eliminate the use of cobalt and are cheaper to produce. This move is part of a larger strategy to diversify battery production and make electric vehicles more affordable. After all, Tesla's ultimate goal is to popularize EVs, and to achieve this, battery costs must drop significantly. But Tesla is not alone in this race. Other companies are also seeking ways to become self-sufficient in battery production, and the market as a whole is evolving rapidly. What makes Tesla's strategy different is its aggressive and integrated approach, which spans from lithium mining to the final assembly of battery packs. This level of control could give Tesla a massive competitive advantage in the coming years. With so many investments and technological advancements, Tesla is getting closer to becoming a global benchmark in battery manufacturing. However, the big question remains: to what extent will the company be able to become fully independent? And how will this shift impact the electric vehicle and energy storage markets? The future of batteries is being written now, and Tesla is at the center of this revolution.